All right, guys. Let's take a look at this homework, and then we are going to PES. Give me a P. No. All right, guys, what questions do you have? 63?
I agree.
All right. You don't. You concur. You concur. Okay, so guys, okay. So guys, question number 63 is about electron spin and things like that. So I'll be honest with you. The answer that I took for question A, part A of 63, frankly, was stolen out of the book. I used it because it was an example of evidence for spin that we hadn't talked about. There's a lot of evidence for spin. It's all over the place. We talked about it a little bit the other day when we talked about the idea, and again, this is, my board shut off just a second. We talked about the idea that if you have an electron that's in an orbit, and we're going to let Bohr be okay for this conversation. If you have an electron that is in an orbit, and we'll just draw it like this, and guys, if the direction of spin is perpendicular, so its direction of travel would be like this. If its direction of spin is perpendicular to the plane of its rotation or of its movement, or if it's parallel to its direction of movement, the energy of that electron is different. It's about angular velocity and momentum and all these different physics things. There's another additional evidence. I don't even know what this says about silver atoms, magnetic fields, but guys, the example, or at least the evidence that we talked about in class, and this was last year, was the idea that if we take electrons and expose them to magnetic fields, anytime you have something with a charge that travels through a magnetic field, it creates a current. You guys understand that, right? That's how we generate electricity. We take a magnetic field and we spin a coil of wire inside of it, driving it with steam or whatever. And guys, that makes a current. Well, the same thing's happening here. If we take electrons and expose them to a magnetic field, those electrons are spinning, they're moving, and as they spin and move, they create a current. And by knowing the polarity of that current, we can figure out if they're spinning clockwise or counterclockwise. There's all sorts of evidence. So, was that enough on 63, or did you want to keep going? Keep going. Okay. So 63b then says, draw an energy level diagram that shows the relative energetic positions of the 1s and 2s orbital. You okay with this? Okay, that's the rungs of the ladder, right? Put 2 electrons in the 1s orbital. Done. And then it goes on to say, draw an arrow showing the excitation of an electron from 1s to 2s. No, this is the arrow showing the move. It says, so literally it says, draw an arrow showing the excitation of an electron. So these arrows are electrons. That's the arrow showing the excitation as it jumps up. No, yeah. Yeah, no, that arrow on the right, I'm just following the instructions, and it says draw an arrow that shows the excitation, so that's... So...
Right there, the 1s, those 2 electrons, those ones that have the 2 electrons.
Yep, so here's your...
1 to 2s and just show them.
Correct. Yep. But that's... Yes, go ahead. Yes, that's a good question. It's a really good question. And so notice the way that this is stated. It says, draw an energy level diagram, which is what we call, we've looked at them like this, right? Reactance, products. These are energy diagrams. And so when and you're going to be drawing a lot of these in this class on the test, because we're looking at energy changes. So the y-axis is energy. The x-axis doesn't really have units, but it's just relative. It could be time. It could be relative position. But the idea is these energy diagrams are simply ways of representing energy change. So this would be exothermic because energy is going down. This could be the 1s and then the 2s, and energy is going in as the electron promotes. It's just a way of visualizing energy. So probably what they would do if this was on the AP test is they would actually give you the grid. They would show you energy, and then they would so they would lead you to, please draw it like this. Absolutely, yeah. They would draw. They would lead you to that, or they would have to accept multiple ways of representing it, because you could also do it like this. So here's electrons in the 1s, and then you could promote an electron to the 2s, and that would be fine too. Yeah, that's fine as well. What else, y'all? Yeah. 8? Yeah. Oh yeah. That got an oh yeah vote from Cole. Let's go. Josh? Oh, he's like a ventriloquist. Oh, yeah. Okay, so guys, on... what just happened? For me? She's up here. Come say hi. You... Has it ever stopped me from interrupting your class? You're not defiling them. You're just amongst them. You. How did you get in? Of course. So you had no problem interrupting Brittany's class.
I thought that, but in the video she was creating, I was like,
No, because that would have sat there for hours and no one would have known you were here. But for me. Well, who? Spencer? 8? Okay. Don't worry about it. Yeah, no, seriously, don't worry. So this was the thing that I showed you very, very briefly last time in class, where we talked about this idea that if you've got the electron, let's do it different. If you've got the electrons like in the 2p sublevel, and the electrons look like that, totally violating Hund's rule, the way that I drew those. We would say that, and we can give these things N, L, M, and S values. So in this case, N would be 2 because it's in the second energy level. The sublevel would be P, but P has the numerical value 1, and then the orbitals number from positive L to negative L to positive L, so that would be -1, 0, and 1. So like that electron would be in the -1 orbital, and then the spin is down, so it's minus. That's what this is about, and they wrote it out of the curriculum, and frankly, I just forgot to take it out of the homework. So frankly, it makes me sad. This is interesting stuff, but it's not necessary anymore, so don't worry about it. What else, you guys? Are we all done? We're good? Okay. So you don't need note. All you need today is something to write with. I printed your notes. Oh, yeah. Again, like Christmas. Oh, yeah. Oh, yeah. More than just the test we're taking next time. I don't know. Okay, so here I go. Don't let me screw this up. Yeah. You really have to handhold this stuff with me. Together we're going to get through it. So, guys, I've already shared with you the very, very contentious history of how PES became a part of what we need to know for this class. Again, I shared with you the fact that I was hyper resistant to this, but then I finally realized that I have to swallow my pride and learn something that seems ridiculous, simply because you need to know it for the test. And then, guys, as I learned this material, I was like, oh my gosh, this is actually really interesting. And so, guys, that's my current position. This is interesting stuff, and frankly, it's fun to teach. With that said, let me explain to you the way that we're going to approach this. So guys, in order to understand PES, the first thing that you've got to understand is just some fundamental stuff about atoms and electrons and the nucleus. And we're going to go over that. It's kind of review, but we're going to use some terms that you need to be familiar with. Then, guys, once we've done that, we're going to start drawing diagrams of atoms, and we're going to talk about the interesting physics, the attractions that take place within these atoms. And then, guys, once you understand all the attractions and all the dynamics and all the physics inside of an atom, we're then going to apply it to PES. And I think you too are going to be interested, and you're going to go, oh, that's actually really kind of genius that this not only works, but we figured out that it would work. And so you should come out of this with a pretty good general understanding of PES. But then, guys, after that, we're going to call time out, and I'm going to show you what you're going to see on the AP test relative to PES, and frankly, it's a little bit of a letdown. You don't need to know the physics. You don't need to know the interesting dynamics that are going on for PES. All that you have to be able to do is draw and interpret PES spectra, and that's how we're going to wrap up the day. So again, we're going to talk about the underpinnings of this, and then, guys, we're going to apply those to PES, and then we're going to talk very specifically about what you need to know for the test. Hello, Preston. How you doing, buddy? So you missed homework, turning it in? But we'll talk. All right. All right. If everything went well, I should have one extra. Wait, did I give you 2? Did I give you guys 4? No, then I guess I can't. Guys, is there an extra one floating around out there somewhere?
I'm using this.
No, but that doesn't explain the extra. Preston, you're late and now you're interrupting. Shame on you.
I'm sorry.
Did somebody get... I think I now know why you're late.
Yeah.
There we go. All right. So, you know what? Isaac, I'm going to leave this with you anyway because you may find that that's not the most efficient way to do that, but I'll let you decide. All right. So, guys, electron spectroscopy. Bottom line is this. What do we use electron PES? Let's just call it PES. Guys, what do we use PES to do? And the answer is figure out the electron structures for atoms. Figure this stuff out. 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p. Guys, PES is one of the strongest experimental supports for the idea that this is really what electrons are doing. So how do we do that? And guys, the answer begins here. We need to start talking about some background information that you need in order to be able to think and talk intelligently about PES. So guys, what are those 3 things? You've got them there in your notes, but guys, let's define them before we get... So understand, your notes are not complete. You're going to be writing a lot. I took a lot of stuff out. So guys, these are the things that you need to know about PES. But before you're ready to do this, we need a place to actually draw pictures. So I'm going to have you draw this in your notes. So guys, off to the right, draw the nucleus of the atom, and then you're going to do the orbitals, the orbits, the energy levels for now. Adding them from left to right. Then guys, you can label the nucleus. And then, guys, as we get started, there are 3 ideas, three fundamental things that you need to understand about atoms before we can get into PES. So, guys, what we're going to do is we're going to talk about the forces that electrons see inside of an atom. And guys, understand, this is the way intelligent people talk about this. Use this if you ever are asked to write about this on the AP test. Guys, feel free to say, this electron sees these forces. That's the way we talk about this. You could think of it as like experience or feels, but the word that we use is see. So, what are the forces that an electron sees in an atom? Well, guys, the first one that we need to talk about is what is called, I forgot. We got to doctor this the rest of the way up. Guys, make this a hydrogen atom. So put a proton in the nucleus and then stick in an electron. So now we can talk about what are the forces that this electron sees in an atom. Well, guys, the first one that we need to talk about is what is called nuclear charge Z. But this is actually an abbreviation that you already know, even from last year. Guys, what does Z represent? The atomic number. So make that connection. Z, and you're welcome to write this down if you want. It's not in the notes. It's not going to come up on the screen. But guys, Z is the atomic number. Do you see the connection? What does the atomic number tell you about an atom? The number of protons. It's the number of protons that gives you the charge of the nucleus. Do you get it? So guys, the idea then simply becomes this. Hydrogen is element number 1. It's got 1 proton, so the nuclear charge is +1. Helium, 2 protons, atomic number 2. Its nuclear charge is +2, and so on. You get the idea? You see how those connect? Okay. Then, guys, the next one that we need to talk about is, and don't turn yours to helium yet. Guys, the next one that oh shoot, this isn't going right. Sorry. Wow. This is all, we'll come back to that in a minute. Guys, the next one we need to talk about is shielding. This is really a mess. Ugh. So guys, the next one that we need to talk about is shielding. And then I'm going to go back and reset this slide, and we're going to talk our way through it. You guys remember shielding from last year? No? No? Go ahead. Were you, Parker? No.
Isn't it like how much? It's like giving off electrons. How much?
We talked about it when we talked about that, but you're not quite there. Shielding? Go ahead. Yeah, so it is about core electrons. But guys, this means so much to me. I just want to go back and show you. This was a magic day last year. General chemistry, where's bonding? Bonding intro. Oh shoot, that's not it. No, that's not where it is. My bad. We got to go back here to periodic trends. Here it is. Oh, you guys even get the new animation. Here we go. There it is. All right. So guys, you remember this? Electronegativity. What is electronegativity? It's the fight over electrons. Here we have a hydrogen nucleus. Over here we have a potassium nucleus. And the hydrogen nucleus reaches out and grabs that electron. What is that force called? It's kind of the nuclear charge. We'll talk in a minute. And then this electron is pulled into the nucleus. But what is that one electron doing? It's pushing back. What do we call that push back? Shielding. Then over here we've got a stronger nucleus pulling harder, but now we've got 19 electrons pushing back. Now you remember shielding? Okay, shielding is that interference. It's that push that is caused by those core electrons. Oh, shoot. Now I got to click through all of this again. All right, we're back here. So, guys, shielding is interference caused by core electrons. Repulsion, interference, repulsion. You pick the word. It's not going to come up in the slides, but if you need to write it down, you can. So, guys, shielding is repulsion or interference caused by core electrons. So then, guys, this brings us to a new idea, an important idea. And that new and important idea, guys, is what is called effective nuclear charge. It is abbreviated Z sub EFF for effective. So, guys, effective nuclear charge is basically, think about this, effective nuclear charge is basically this minus that. Think through that. Effective nuclear charge is basically the nuclear charge minus the shielding. Do you see how that fits together? If you don't, and don't write this down yet, we're going to write in a minute. But guys, the idea is this. If we look at a lithium atom, and if you're not understanding effective nuclear charge, let's use lithium. Don't write it down, but just watch. So guys, what is the nuclear charge of a lithium atom? What's the nuclear charge? 3 protons, right? So this electron right here sees the attraction of 3 protons. This electron right here sees the attraction of 3 protons. But guys, what about this electron right here? Does it see the attraction of 3 protons? And the answer is no. The reason is because these 2 intercore electrons are actually pushing on that electron. So the effective nuclear charge that this electron sees is the nuclear charge minus the shielding of the core electrons. So guys, this electron out here sees a decreased effective nuclear charge because of the shielding of the core electrons. Does that make sense? Ask questions, yeah.
So would it be just a positive 1 charge?
Yeah, and Maddie, that's a really good question. And the answer is that's not math that we're going to do. So Maddie's question is, so is it just +3 minus 2 is 1? And the answer is no. And you might suspect why, because these electrons in the 1s sublevel are not just chilling right there, right? And it's not exactly the pull of a proton is canceled by the repulsion of an electron. It's way more complicated than that. So, but actually, interestingly, now we can model it. We actually have computers that are fast enough, and we can write code that is complete enough that we can actually predict the effective nuclear charge on that electron, but it's way more complicated than just 3 minus 2. With that said, just a second, with that said, you do need to understand that the effective nuclear charge for this electron is less than these. That's all you've got to understand, is that the pull that electron feels is less than the pull that these feel. Okay, and guys, that's where we're going to go with this in just a minute, is we're going to talk about increasing and decreasing pull. Yeah.
Why are the electrons
Yeah, that's a really interesting question, right? So, and it really doesn't have anything to do with this, but we can talk about it briefly. That was actually one of, so guys, Spencer's question is, why are the electrons not then in the nucleus, right? Because we've got a positive charge here, we've got a negative charge there, why don't they just get sucked into the nucleus? Is that kind of your question? So the answer was confusing at first. But we can ask a different question. Why is the Earth not being sucked into the sun? In the same way that the Earth travels around the sun, electrons travel around the nucleus. So why is it that the Earth doesn't get sucked into the sun, And then we can talk about why do electrons not get sucked into the nucleus. Because remember, when Bohr suggested the planetary model of the atom, it was based on the solar system. And there was actually a name for your question. It's called the ultraviolet catastrophe. Because it turns out that they did the math, and if electrons started falling into the nucleus, it would release ultraviolet light. And so they were looking at this and they were going, wait, why are these electrons not getting sucked into the nucleus? It turns out the answer is different than the Earth and the Sun. So let's talk about it. So why is the Earth not being sucked into the Sun? And the answer is because if this is the Sun and if this is the path of the Earth is moving in this direction. It's because it's orbiting. And because it's orbiting, as it moves in this direction, the curvature of the Sun is always falling away from it. So we are in fact being pulled towards the Sun, but we're moving in this direction at exactly the right speed that this distance doesn't change. That's how orbit works. That is not why electrons are not getting sucked into the nucleus. The reason electrons are not being sucked into the nucleus is because they're not really there. Right? Yeah, I mean, seriously, that these electrons, when we talk about these shapes in these orbits, the electrons actually don't follow these paths like the Earth around the Sun. All these spaces are positions of probability that are supported by these wave-like structures. And so, really the answer is because the electrons aren't really there, but if you'd like another answer that's maybe a little more reasonable, it's because these orbits are supported by the wave-like characteristics of these spaces, and it holds them out and doesn't let them fall in. So that's actually, I know, right? That's actually the answer. Okay, so guys, go ahead.
So I understand that these two electrons
Yeah.
are static, so their position is not the same
Mhm.
place.
Yes.
But like this electron, like over here,
Yeah.
never falls into the first one.
That's a really interesting question. So can this electron fall into here? And the answer is no. And that's the whole idea with the Pauli exclusion principle, that this space can only hold two electrons. And so if this electron was to fall down here, remember the Pauli exclusion principle says no two electrons can have the same four quantum numbers. And if this electron were to fall into this orbital, it would have to become one of these two electrons, and that's not possible. So the only way that this electron could fall down to here is if one of these electrons left first. And that's actually, do you guys remember when we talked about how they generate x-rays in a dentist office? That's actually what they do, is they take tungsten and they hit tungsten with so much energy that one of its core electrons leaves, and then one of its higher energy level electrons falls down to replace it, and that releases x-rays. But the only thing that allows it to do that is because one of those electrons got kicked out, creating space. What else, you guys? Yeah? That's a Evan, that's a brilliant question. So why is it that the inner electrons go, but the outer ones don't? And the answer is because they blast it with just enough energy that because remember quantized energy, right? These energy comes in packets, and they blast it with just enough energy that the only electron in the system that can absorb the energy is this one. The other ones don't know what to do with the energy because it doesn't have the right amount of energy to get those electrons to leave, and therefore it doesn't absorb it. The thing that's really interesting is your very question is one of the fundamental issues with PES, which is what we're talking about, because what you're going to find out in a minute is what we do in PES is we blast these atoms with enough energy that any of them can leave. And so in fact what happens is all of them leave. And we're going to talk about that in just a second. So, yeah.
Sorry, so you said that children is caused by four.
Yeah.
So how do you identify them?
Great question. So, guys, let's do this. And guys, forgive me, these animations are a disaster. But now that we understand these ideas, rather than do the animation, and do this with me. You want to write this into your notes. Do this with me. So guys, I think you've already done this, right? Let me get nucleus out of there. Even that's in the way. Okay, so guys, I'm not going to try to do the animations because they're a mess. Let's just do this together. So protons, let's go 1 and then an electron, okay? So this is a hydrogen atom. So let's talk about the forces that electron sees. So guys, what is the nuclear charge in a hydrogen atom? 1. How much shielding is there? None. There's only one electron. There is no shielding. So guys, the effective nuclear charge that electron sees is the pull of this one proton. Does that make sense? Okay, now guys, do this. Add another electron and then make this a 2. However you do that, I'm just going to write it over the top. Now it's a helium atom. Same question. What is the nuclear charge? 2. What is the shielding? 0. So now guys, what about this? Do the two electrons in helium see a higher or lower effective nuclear charge than hydrogen? Higher, because now we've got 2 protons. And guys, don't think of it like this. It's not like one of these electrons is being pulled on by one of the protons and the other electron is being pulled on by the other proton. Those 2 electrons see the pull of 2 protons. And so both of these electrons see a stronger effective nuclear charge. And guys, as a result, the atom gets smaller. Write that in. Helium is smaller than hydrogen. Guys, you learned that last time in class. Helium is smaller than hydrogen. The reason is because 2 protons pull the atom further together. Do you remember when we talked about that last year? If you don't, let's remind ourselves. So guys, as we go left to right across a period, the atoms get smaller. So it gets smaller, 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 smaller because the nucleus gets stronger. Do you guys remember that idea? As we move down, they get bigger because we're adding energy levels. And as we move to the right, they get smaller because the nucleus gets stronger. That's what we're talking about right here. You guys good? So let's make sure. Which then is a smaller atom, helium or hydrogen? Helium. Okay. Now guys, let's do this. I know I have an advantage over you and I'm going to take advantage of it. I'm going to clean this up. So now let's go 3 protons and now let's make this a lithium atom. So 1 and 2 and then 3. So now guys, this. Looking at the 2 electrons that are in the first energy level. Talk to me about the force that those electrons see compared to helium. Compared to helium, and guys remember helium is 2 protons and 2 electrons. So guys, compared to helium, will the effective nuclear charge that these electrons see be greater or smaller? Greater. Do you see why? Guys, these electrons do not see any shielding, but they see a nucleus with 3 protons. So these electrons are going to be moved even closer to the nucleus than they were in helium. Does that make sense? Just a second, Isaac. Does that make sense? Now, guys, let's talk about this. What about the pull? What about the effective nuclear charge that third electron sees? Will it be greater or less than these electrons? Why is it less? Because of shielding. Does that make sense? Okay, Isaac, go ahead. A little bit. It's a really interesting question, but we don't need to worry about it relative to what we're doing with this. The important force is the pull of the nucleus and then shielding. Yeah.
So that's that's like the S orbital I was referring to. So when you get bigger, does the S orbital get smaller? Because I thought it got bigger.
No, it actually gets smaller. And so let's draw some pictures. This will be interesting. I wasn't planning on this, but let's do this. Maybe you don't try to draw them, but watch. So for example, this is a hydrogen atom, and we've got one electron right here, and that's hydrogen. Okay. Now let's do helium. So 2 protons, and we're then going to add another electron, but what will happen to the size of that? It's going to move this way, right? And so maybe it looks like this, and that's helium. So now let's go to lithium. And so lithium then now has 3 electrons. Where are these 2 electrons going to be? Even closer. So these electrons are going to be even closer because they don't experience any shielding and the nucleus is stronger. And then this next energy level is going to be out here. And so this would then be lithium. Now what about this? What if we then go to beryllium? And I'm sort of out of space. But if we go to beryllium and make this 4 protons, what's going to happen to these guys? Even closer. What's going to happen to these guys? Even closer. So these are going to move in, these are going to move in, and then there will be a second electron there. But what about this? Talk about the pull that these 2 electrons see. Same or different? Yeah, just these 2 electrons compared to each other. It's the same. So these electrons see the same pull, but it's stronger because it's beryllium with 4 electrons. So the idea then is that, oh shoot, I wish I could have compared to 3. Here, let's do it again. So 3 protons, we've got this, and we've got this, and 1 and 2, and this is lithium. So then if we go 4 protons, this is going to be closer, and this is going to be closer because they're all getting pulled in by the stronger nucleus. You guys okay with that? Guys, that's PES. We're done. Seriously, that's it. That's all there is to PES. The fundamental idea behind PES is all you're doing is mapping the attraction that these electrons have for the nucleus. So the idea is this. If you look at a hydrogen atom, that hydrogen atom's electron has some attraction. When we go to helium, the attraction that those 2 electrons sees is greater because helium's nucleus is more positive. When we go down to lithium, element number 3, the attraction that these electrons see is even greater, and then we've got a 3rd electron out here, but because it's in the next energy level, its attraction is less. That's what we talked about here. Then we go to beryllium, 4 protons, even greater attraction, and then we've got these 2 electrons that see a greater attraction than the 1 electron in lithium because now we've got 4 protons. Guys, that's the logic behind PES. The question is, how do we make the measurements? And we'll do it in a minute. But guys, that is the logic behind PES. Yeah?
Wouldn't shielding kind of be messed up because the dumbbells are silent?
Absolutely. And so there's a lot of different dynamics with this. But even if we were to draw these like a sphere and then a bigger sphere and then the dumbbells, so this would give us the first 2 energy levels, right? If we're then in a 3S, so imagine that we were looking at something like sodium. So this electron is going to see a bunch of shielding, right? And the shielding it's going to see is from the 1s and the 2s and then the 2p's. And yeah, those 2p's are dumbbell shaped, but they're still core electrons and they still provide shielding. Maddie, another reason why the math isn't as easy as the subtraction, because you're absolutely right. Some of these orbitals aren't even spherical, but they still shield. And so you've got to, what we need to understand is that core electrons shield regardless of what the shape of their orbital is. Is that okay? Kate, you were going to say something.
Yeah, so how come in the same row on the periodic
Yeah.
table, the increase of like valence electrons is valence shell like closer?
Smaller, and that's exactly the point. That's this, that as we add protons to the nucleus, it's pulling everything tighter together. So you're right, we're adding electrons, right? 1 electron, 2 electrons smaller, 3rd electron a little bit bigger because now we're in the 2nd energy level. So yeah, so as we move from helium to lithium, it does get bigger because we're adding an electron to a bigger energy level. But then as we move to beryllium, it's getting smaller because the nucleus is getting stronger. And that would just continue to be the case all the way over to neon. Is that okay? Guys, what else do we need to talk about? Okay, so this then is the jumping off point. Guys, and Cade did a great job of letting us wrap our arms around this. Guys, this is the chemistry. This is the physics behind PES. The idea is that as we add electrons and protons to an atom, it gets smaller. The stronger nucleus pulls things tighter together. And then it's also about shielding, as these core electrons provide a little bit of shielding or interference with these outer electrons. But guys, what we've done up until now is we've related this to size, right? As we go down, the atoms get smaller. What we've got to do is relate it to attraction. So check this out. Which electron is more attracted to the nucleus? This one, we'll call that electron 1, or this electron, electron 2. Which is more strongly attracted to the nucleus? 2. Why? Nucleus is stronger. So guys, there's a direct relationship between size and attraction. So this makes sense, right? The closer an electron is to the nucleus, the more attracted it is to the nucleus. Doesn't that make sense? But guys, we're not going to use the word attraction. Turn the page. Instead of the word attraction, we are going to use the term, and hold on, I got to click like crazy to catch up with you guys. We are going to use the term electron binding energy. So guys, this is where this becomes about PES. So what are photoelectrons? They're electrons that are ejected from a substance due to energy being added in the form of photons, many times X-rays. But guys, what does this have to do with electron structure? And it's all about what is called electron binding energy. Do you have the definition? So guys, electron binding energy is the amount of energy that is required for an electron to overcome the attraction of the nucleus and go away. It's the amount of energy needed to overcome the attraction of the nucleus and therefore go away. But guys, we already know that the attraction of the nucleus is called the effective nuclear charge. So electron binding energy, how tight the electron is bound, is a measure of the strength of the effective nuclear charge. Now you're going, wait, I'm not sure if I understand that. So guys, let's bring it back to this picture. So let's do this. So looking at our hydrogen atom and then talking about pulling this electron off. How much energy does it take to get rid of that electron? And the answer is electron binding energy. So if we can add enough energy that we can unbind the electron, then the electron goes away, and that's called electron binding energy. Now guys, let's look at this electron. How much energy does it take? How much electron binding energy does it take to get rid of that electron? Well, here's the question you got to be able to answer. Which one takes more? Electron 1 or electron 2? Which one takes more energy to get rid of? Electron 2, because it's more tightly bound. Why is it more tightly bound? Because the nucleus is stronger. We also think about this as size. So the closer an electron is to the nucleus, the stronger that it's bound, and the greater the amount of energy that we've got to add in order to make it go away. Does that make sense? Is that okay? Guys, that's all electron binding energy is. Yeah. That's an interesting question. So fundamentally nothing. So we can think of this as being like ionization energy, It's just that when we do this with PES, we call it electron binding energy because it fits into an equation I'm about to show you. But if you want to think of it as being the same as ionization energy, that's fine. Technically, it does come back to what Evan mentioned a minute ago, which is that when we think about ionization energy, we think about the energy to remove the outer electrons. When we think about electron binding energy, it could also be the core electrons as well. And we'll talk more in a minute. You guys okay with this idea of electron binding energy? Okay, so guys, let's bring this all together then, and let's take a look at what this has to do with PES. So there's actually the answer, for our purposes, the same as ionization energy. But guys, do this. Switch pages with me again. This is the equation that drives PES. But guys, you do not need to understand this equation. You don't need to know this equation. The only reason I share with you this equation is because it allows you to really understand how PES works. And this is the way that this goes. You should label these with me. So guys, H nu, you already know that that's the energy of a photon. You know the equation. Energy is equal to Planck's constant times nu. So guys, that over there represents the energy of an incoming photon. And for our purposes, these are going to be X-ray photons. Higher energy than visible light or ultraviolet. Then guys, you already know EBE. That's the electron binding energy, which is the amount of energy needed to eject the electron. How much energy do you need to add to the electron to get it to come unbound? That's called electron binding energy. And then guys, KE is kinetic energy. And you already know the kinetic energy is equal to 1/2 mv squared. Now guys, we're going to bring everything that we just talked about together. We're going to talk about all of these drawings that we talked about previously, and we're going to tie this all back together to PES so that you not only understand how this works, you understand what it's representative of. But guys, in order to do that, we need to draw our picture again. So draw your picture again. Start from scratch. Draw your picture again like this. This is where this got really interesting for me. It was sort of a breakthrough moment where I felt like I finally understood PES. So guys, this is obviously not drawn to scale, but I'm going to ask you to add an additional thing to your drawing. I'm going to make this stand out, so I'm going to get a really thick drawing utensil. And guys, I'm going to put this over here. I would encourage you to do this as well. And the thing that you just drew is an electron detector. Now guys, let's actually talk about the scale. You understand that all of this is an atom, right? So it's the nucleus with its orbitals around it. And then guys, from this atom over here to the detector, it's about 1 meter. So what we're really talking about is a sheet of, well, either a sheet or a gas, or maybe it's a vessel of hydrogen or a vessel of helium or a sheet of lithium or a sheet of beryllium. But guys, what you've got is over here you've got your sample, and then you've got some distance to where you've got an electron detector. So obviously it's not drawn to scale. This represents the size of an atom, and the rest of that represents a detector about a meter away. So guys, with that said, let's talk about how this crazy thing works. And guys, this is how this works. And I would encourage you to not write this down until we're sort of at a point where we can talk about it. But guys, we're going to use some funny numbers, but it'll work. So guys, this electron is attracted to the nucleus, right? What do we call the amount of energy that it takes to overcome that attraction? The electron binding energy, right? Okay, so let's say that we don't know the electron binding energy for the electron in hydrogen, but we would like to measure it. Well, guys, this is what we do. What we do is we take an X-ray source, and they call it pulsing. What they do is they pulse the sample, in this case a vial of hydrogen gas. They pulse the sample with X-rays. They literally go, and they take an X-ray, if you will, of the sample. And guys, we can figure out the energy of these photons. How do we figure out the energy of the photons? We know Planck's constant, and we can measure the frequency of the energy. And by knowing that, we can figure out the energy, because energy is equal to Planck's constant times the frequency. So, say that this, we're just going to use a huge number, say that that is a 10 joule photon. It's not. But say that it's a 10 joule photon. Well, guys, what is that energy going to do? Well, and actually I should have drawn it in this direction. This electron is going to absorb all 10 joules of that energy. And guys, when this electron absorbs that energy, what's going to happen to it? What happens to electrons when they gain energy? They start moving up and up and up and up and up and up, and eventually that electron is going to get to energy level infinity, and at that point it's no longer bound to the nucleus. And then, guys, this electron's going to go woohoo, and it's going to go flying across the detector. It travels about a meter, and then it hits this detector, and the detector goes, got it. Now, guys, all we've got to do is measure the time that it took between the pulse over here and the detection over here. And by knowing the time that it took this electron to travel this distance, we can now figure out the electron binding energy. How does that work? And guys, the way that it works is this. We know how much energy went in. How do we know? Because we know Planck's constant and we know the frequency of the X-ray. So guys, this we know. We know the amount of energy that went in. We can also measure the kinetic energy of the electron coming out. And how do we measure the kinetic energy? Well, we need to know the mass. But we know the mass of an electron. And then we need to know the velocity of the electron. But guys, velocity is distance divided by time. We know the distance and we measure the time. Does that make sense? So we know the distance, we measure the time. Distance divided by time gives us velocity. We do this math, and now we know the kinetic energy. So guys, now let's use our funny numbers. So say that we put 10 joules of energy in, and we measure the kinetic energy of that electron, and that electron comes out with 7 joules of kinetic energy. What's the electron binding energy? 3 joules, that's it. We now know that this electron was bound to the nucleus with 3 joules of energy. Do you see how that works? Guys, that's all there is to PES. You put energy in, you measure the amount of energy that came out, and the difference between those two is the electron binding energy. Isn't that cool? Go ahead.
So just to
Mm-hmm.
they have to struggle through the energy fields, and then when they energy fields, that's the constant velocity. Is the time to get through that just not?
It's actually, understand it's quantum. Remember that when electrons travel distances in an atom, it happens instantaneously. So really what happens is this electron goes from here. You can kind of think about it like pulling against a force, and it's going, gonna make it, gone. And then it just takes off, right? So as it's leaving, it's overcoming that attraction, and then when it gets far enough away, energy level infinity, that the attraction falls to zero, then it accelerates, and that acceleration we can then use to figure out velocity and kinetic energy.
I'm just saying that when you're measuring the time,
Yeah.
like, does the time it take
No, because
instantaneous?
it's instant. It's literally instantaneous.
Because that's not the same velocity that is moving after it leaves level infinity, but the time it takes is
And in this case, it's instantaneous. Yeah, go ahead. No, and that's where we're going now. So what do these spectra look like? But guys, before I can take you to, so now we're ready to talk about what are you going to see on the test. So guys, do this with me. I'm going to clean, questions about how PES works? Is that okay? Okay, now do this. So we're going to use, again, funny numbers, and let's say that this electron is bound with 3 joules of energy. It's not, but let's say. So now, guys, let's make this a helium nucleus. So if this is a helium nucleus, now we've got 2 electrons. What will the electron binding energy for these 2 electrons be relative to 3? Greater or less? Greater. So it will be greater because this nucleus is stronger, but what do we know about the electron binding energies for both of those electrons? They'll be good, yeah? Now guys, let's do this. Let's now go to lithium. So now we've got 3 protons. So what will the electron binding energies for the first energy level electrons be? Even greater, right? So guys, relative to helium, the electron binding energies for these will be even greater. But then guys, what about the electron binding energy for that guy? Less than the other ones. But then let's do this. Now let's go to element number 4, which is beryllium. So guys, beryllium has got 4 protons and 4 electrons. So what will the electron binding energies for those guys be? Even greater. What will the electron binding energies for these 2 be compared to the 1 electron that was in beryllium? Greater and the same, right? So now what if we add a 3rd electron and we make this, a 5th electron and make this boron? Now these will go up and all of these will go up and they will be the same. Do you see the logic of what we're saying? Guys, this is represented then like this. And so here's the answer to your question. How does a PES machine then report on this data? And guys, this is how. It looks like this. So let me show you the PES spectra for hydrogen. Do you see it? Here's the way that this works. So guys, we have increasing ionization energy. Wait a second. Oh, shoot. This was the fight that happened. Remember when I told you that the high school woman and the college professor guy almost got into a fight? It was over this. They were fighting over which side is higher energy. This is the one that's right in our notes. So guys, I'm going to take this away just for a second to make sure I'm not sending you bad info. Hold on. No, it's not. Oh, wait a second. No, we're okay. Yeah, okay. So, guys, soak this in for a minute. So look at what we've got. On the y-axis, we've got numbers of electrons, and on the x-axis, we've got ionization energy or electron binding energy. On the AP test, you'll see electron binding energy. But guys, notice what we have. As we move to the left, we've got stronger and stronger electron binding energies. So, guys, the best way for you to think about it is like this. This over here represents the nucleus. And we've got an electron that is some distance from the nucleus, because remember, distance and attraction are similar. They're analogous. So the further away an electron is, the less it's attracted. The closer the electron is to the nucleus, the more it's attracted. And you guys understand that this is actually backwards to what we drew here, right? In our pictures, the nucleus was on the right. Now the nucleus is on the left. Is that okay? So now let's do this. Guys, this is hydrogen. So here's the nucleus, here's this one electron for hydrogen, and it's got this attraction to the nucleus. And then notice, guys, the height of the spike represents how many electrons are present, and in this case it's 1. Here then is the question. Guys, what is going to happen when I change this to helium? How's it going to change? First of all, let's talk about attraction. Are the electrons in helium more or less attracted than the one electron in hydrogen? More attracted. So what is that going to do to the location of the hump? It's going to move to the left because that's increasing attraction, and we also understand it's smaller, so it's going to move to the left. But how many electrons are there in helium? 2, and how will that be represented here? The spike will be twice as high. So this then, guys, let me get out of the way so you can see. This then is the PES spectrum for helium. Do you see it? Hydrogen, helium. What does it mean that it moved to the left? Stronger attraction. What does it mean that it got twice as tall? 2 electrons. Now, guys, what's going to happen if I move to lithium? What's going to happen to this? It's going to move even further to the left because now we've got 3 protons. But then, guys, what else are we going to see? Another spike, second energy level, less attracted with 1 electron. So, guys, check it out. Lithium. Do you see it? So what are these 2 electrons right here? First energy level electrons. What are these guys over here? The 1 second energy electron. Now what if I go to beryllium? How's it going to change? What's going to happen to this? Going to move to the right. What's going to happen, or to the left? What's going to happen to this? Move to the left and get taller. So let's go to, well, I want to get out of the way. So now we move to beryllium. Is that what you expected? So lithium, beryllium, moved to the left and got taller. What about boron? Further to the left and even taller? The p orbital is different than the s. Remember, guys, the p orbital has slightly more energy than the s. This was some of the first experimental evidence that showed us that the s and p electrons are not the same. So, guys, this is the 2s and this is the 2p, and together they make up the second energy level, but this is accurate enough that we can see the difference between the s and p electrons. Do you see that? Then, guys, let's keep going. Let me clean up this mess. So where we are right now is we are on boron, right? Boron, 5 electrons. So we're on boron. What's going to happen if we go to carbon? What direction are all of these going to shift? To the left. What's going to happen to that little guy? He's going to double in size. So we're going to go carbon. Then what's going to happen with nitrogen? Even taller. Oxygen, fluorine, neon. Do you see it? Guys, they keep getting taller and taller and taller. But then, guys, what's going to happen when we go to sodium? Everything's going to shift to the left. What's going to happen to the height of these? Nothing, right? Because when we go to sodium, we're now in the 3rd energy level. So what are we going to see way over here? A new one that's only 1 tall. Huh? Yeah? And then magnesium. Then what about when we go to aluminum? Will this spike get taller? No, we're going to see another little dude, huh? And then silicon, phosphorus, sulfur, chlorine, argon. Do you see how that all relates? So guys, what are you going to see on the AP test? And they'll give you something like this without the little numbers up above. They won't give you these, but they will first of all, but what they may do is label them A and B and C and D and E, and they will say things like, what element does this represent? And all you got to do is add it up. 2 plus 2 plus 6 plus 2 plus 6, whatever that, and that's its atomic number, right? But then it might ask you, what do these electrons at peak B represent? And then we would go 1s, 2s, 2p, 3s, 3p, so we would know that these are 2s electrons. So guys, but they'll also ask you comparisons. They would say something like this. So what if we go back to beryllium, which looks like this, and they would say, this is the photoelectron spectrograph for beryllium. What would the spectrograph for carbon look like? And then what we would need to do is draw this further to the left, this further to the left, this further to the left, and taller. Does that make sense? Guys, what questions do you have? This is what you need to know about PES. But again, this is what they're going to hold you accountable for PES, is just interpreting and then redrawing spectra. You guys okay? Okay, so what then are we going to do with this relative to homework? And guys, the answer is this. In order to be ready to perform on this on the test, what I've found helpful is simply for you to do this. So guys, your homework then is to take this and fill it in. So ionization energy or electron binding energy, high energies are on the left, low energies are on the right. But what you're going to do is you are going to draw these for, the first, through neon. For the first 10 elements on the periodic table, you're going to draw their PES spectra. Now guys, it's up to you how you do this. You could change colors and try to draw them all on the same axis. You could draw 10 separate axes. Realize though that you've got to be able to see relative positions and relative heights. I would suggest just get a blank sheet of paper, put one axis on there, and then just draw them all. You'll see that in my answers I sort of compromised a little bit. But guys, really, if you can do this, you're where you need to be relative to this material for the test. So, guys, anything else with PES? Kind of interesting stuff, at least to me. We good? Yeah? No. So you don't need to know the values. Although it's interesting, on, what year is it, 22? So on the 21 test, the test that we just took, there was a PES question on there, and it was interesting the way they did it. Let me show you. So for example, this, and you can see that they gave you the numbers, right? And so I mentioned before that maybe they might say, what do these electrons represent? And the answer is the 1s sublevel. But when they referenced it on the test, they didn't draw like an arrow with a letter. They said, what does the peak at 19 kilojoules per mole represent? So at that point, you had to be able to read it off the curve, realizing that this is a logarithmic scale, so it goes 1, 10, 100. But it wasn't even close. It's clear that these aren't 19 because that's 1. So it's greater than 10 and less than 100, so it had to be that. But they referenced the peak based on its energy. And then you just had to be able to find it on the axis. But it wasn't even close. It was clearly that one, but it did still trip some people up. But you don't need to know any of those values. You don't need to know the PES equation. All you need to know is the fundamental logic behind how PES works, and then you got to be able to draw and interpret PES spectra. That's it. You guys good? Okay, so I'm going to stop recording. Guys, we're going to take a break, and then